This video explores the topic of stress factors and experimental reliability within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. The operational model defines how the system will perform under real operating conditions. Its main purpose is to ensure that project targets are met and that performance can be verified against contractual requirements. It also provides a quantitative basis for reliability and availability assessments, supporting both design decisions and logistic planning. To build an effective operational model, engineers must first understand the failure modes and associated failure rates, since these determine the system's expected behavior and performance over time. Component reliability depends on multiple interacting factors. One of the most important is the operating profile, which defines how often and under what conditions a component is used: continuous, intermittent, or sporadic operation. Each profile introduces different levels of mechanical, thermal, and electrical stress, directly affecting the component's lifetime. In addition to operational factors, environmental conditions play a crucial role. Factors such as temperature, humidity, vibration, and contamination can accelerate aging and degradation mechanisms. Even storage conditions, before a component is put into service, may influence its initial reliability. Therefore, when defining the system operational model, it is essential to include both the duration and intensity of environmental stress. This allows engineers to obtain a realistic estimation of component behavior and to predict potential failure modes more accurately throughout the system's life cycle. The system operational model expresses how a component's failure rate depends on its technological characteristics and on electrical, environmental, and thermal stress. These influencing factors reflect the actual conditions in which the system operates. To develop a reliable model, it is essential to understand both failure modes and mechanisms, since they are directly linked to the stress applied during operation. Failure mechanisms are closely related to the stress applied to a device. These stresses include both the operating conditions and the environmental influencing factors. Depending on the operational context, the combined effects of these factors may lead to different types of failures. The main influencing factors can be classified into three categories. About climatic factors, an increase in ambient temperature reduces the ability to dissipate heat. This affects not only the behavior of electronic components, but also other types of components, such as the insulation systems of electrical machines. Mechanical factors include shocks experienced during installation and transportation, as well as vibrations to which devices are subjected during normal operation. Electrical factors include electromagnetic interference, either due to power supply characteristics or mutual interference between nearby devices. The reliability of a system strongly depends on how its materials and components are used and qualified. For this reason, the development of reliability models must be supported by standardized parameters that guide the selection and qualification process. International standards, such as those defined by ETSI and IEC, play a crucial role in this context. They establish the environmental and operational limits, including temperature, humidity, vibration, and shock, that components must withstand during testing and real operation. These references ensure comparability, quality, and consistency across different industrial applications and environments. The table refers to the standardized normal environmental conditions. The temperatures reported in the table represent the average or reference values corresponding to the central point, barycenter, of a specific diagram that depicts the possible combinations of air temperature and relative humidity, commonly known as a climatogram. In the climatogram, several zones can be identified. An inner zone, representing the environmental conditions encountered during approximately 90% of the time. An intermediate zone, corresponding to normal limiting environmental conditions, and an outer zone, representing exceptional environmental conditions, for example, a failure in the air conditioning system if present. The proper functionality of the equipment must be ensured within the intermediate zone, while in the outer zone, a reversible degradation of performance is acceptable. It is worth noting that reliability databases also refer to a classification of operational environments through the parameter PI-E environmental factor. It may seem possible to define a direct relationship between the applied stress and the strength of a component, theoretically eliminating the failure condition. In reality, both load and strength follow statistical distributions, not fixed values. By modeling these distributions, we can analyze how their overlap determines the probability of failure. Assuming a normal distribution, although studies in the literature also consider different types of distributions, it can be hypothesized that reliability depends on the distance between the tails of the two distributions. This distance can therefore be used to define a safety margin. In practice, it is the analysis of the characteristic parameters of the distributions, namely the mean and the standard deviation, that allows the quantitative definition of this margin. Now let's consider the stress-strength interference model, which is a foundational concept in reliability engineering. On the left, the load distribution represents the applied stress. We visualize this as a curve to account for the inherent variance in operational conditions around the mean expected load, L. Conversely, the strength distribution on the right represents the component's physical capacity. This distribution accounts for material variability and manufacturing tolerances around the mean strength, S. The critical observation in this figure is the complete lack of overlap between the two curves. The extreme upper tail of the load distribution does not intersect with the extreme lower tail of the strength distribution. This definitive separation signifies a high safety margin, SM, demonstrating mathematically that even under worst-case operational conditions, the probability of component failure is statistically negligible. It is possible to define two indices, the safety margin, SM, and the loading roughness, LR, that take into account the shape of the stress distribution. In reliability analysis, the overlap between the stress and strength distributions determines the probability of failure. The closer they are, the higher the risk. However, the total number of failed devices also depends on how these distributions are shaped. Wider or skewed distributions indicate greater variability, leading to a higher likelihood of failure events. This figure illustrates three different situations describing the relationship between stress and strength distributions. In case A, we have the ideal condition where the two distributions are well separated. No overlap means no probability of failure. In case B, the safety margin is smaller. Although the stress distribution is narrow, the strength distribution widens, leading to a small overlap between the two curves. This results in a limited probability of failure, affecting only a small fraction of components. In case C, the situation becomes more critical. The overlap between stress and strength distributions increases significantly, meaning that a larger number of components are likely to fail under higher stress conditions. These observations are very useful in quality control when it is not possible to test the entire batch. For example, in systems with many electronic components, overstress testing can be applied to identify and eliminate intrinsically weak units. This principle forms the basis of screening tests, designed to detect and remove early life failures corresponding to the initial region of the bathtub curve. Building upon the static model we just examined, this slide introduces a critical new dimension into our reliability analysis, time. On the left side of the graph at time 0, we observe a scenario identical to our previous discussion. There is a clear, definitive separation between the component's inherent resistance or strength, denoted here as R, and the applied operational stress, denoted as C. Initially, our safety margin is robust. However, as the text notes, assuming a device will maintain these exact characteristics indefinitely is an idealized concept. In real-world applications, components inevitably degrade. If you follow the trajectory of the upper R distribution moving to the right, you will notice a downward-sloping dashed line. This visualizes the degradation of the component's resistance over time due to material fatigue, wear and tear, and environmental aging. While the applied stress, C, remains relatively constant across the timeline, the degrading resistance gradually closes the gap. Eventually, on the far right, we see the two distributions begin to intersect. This overlapping region represents the exact point where the probability of failure emerges and begins to increase. Ultimately, our primary engineering challenge is predicting exactly when this critical intersection will occur. To accurately plot this degradation trend, theoretical assumptions are insufficient. We must validate our analytical models with rigorous empirical laboratory testing. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.